The universe is a wondrous place, but what makes it all tick? What holds it all together and stops everything from just flying off into, well, space? In this video I'm going to have a beginner's guide look at the fundamental forces that hold the universe together. Let's find out more. This is another video that was suggested to me in a comment, so thanks Jonathan for the suggestion. There are a number of fundamental forces, or interactions as they tend to be called, and I'm going to take each of them in turn and explain what they do. They're called fundamental because they can't be resolved into other simpler forces or interactions. For instance, the force of friction can actually be explained by using another force called electromagnetism. Electromagnetism, however, can't be explained using any simpler force, and so electromagnetism is one of our fundamental interactions, but more about that later. The interactions that I'm going to look at today are electromagnetism, that I've just mentioned, the strong interaction, which is sometimes also called the strong force or the strong nuclear force, the weak interaction, or the weak force or the weak nuclear force, and gravity. But gravity's a bit strange, so I'll leave that till the end. Let's start with a strong interaction. This works at very small scales, and at those scales it's very strong, hence the name. The strong interaction is responsible for holding protons and neutrons together. Protons and neutrons are the particles that make up most of the visible universe. And protons and neutrons are made up of even smaller particles called quarks. A proton is made up of 3 quarks. 2 up quarks and a down quark, and it's the strong interaction that holds these quarks together. Similarly, a neutron is made up of 2 down quarks and 1 up quark, and again the quarks are held together by the strong interaction. So why do we need the strong force to hold these particles together? Well, originally physicists wondered how atoms hold themselves together. Protons are positively charged, and the nucleus of an atom has got lots of protons in it. We also know that like charges repel each other, a bit like the like poles of a magnet repel each other. And physicists wondered why the nuclei of atoms don't fly apart, because of all the positively charged protons in them repelling each other. The strong force was then proposed as a solution to this problem. Further experiments found that not only did the strong force hold the nucleus together, but also held the quarks inside the protons and neutrons together. And it was found that actually it's the holding of the quarks together that the strong force actually does. That's its main job. The strong force only works over very short distances, about the size of a proton. However, a side effect of the force is that some of it, leaks, for want of a better word, beyond the boundary of the proton or the neutron. And this is called the residual strong force. And this is stronger than the repulsive force of the like charges on the proton, and so holds them together. This residual force, though, doesn't extend very far, and can only really hold adjacent particles together. The repulsive force of the different electrical charges diminishes more slowly, and therefore can act across the whole of the nucleus. This is why as the nuclei get bigger and bigger, the strong force is less able to hold the whole nucleus together. And as they get bigger and bigger, there comes a point at which the nucleus becomes more easy to rip apart. And this leads us to nuclear fission, and I'll get to that in a bit. And here we come to an interesting feature of these fundamental interactions. There are particles associated with the interactions, and these particles carry the interaction or force. If we look at the particles that make up the universe under the standard model, we can see that there are the quarks here. Quarks are really interesting, and I'll be doing a video on those soon. We also see the leptons here, and leptons includes very small particles such as electrons and neutrinos. We can also see the enigmatic Higgs boson. It's the Higgs field that other particles interact with to give them mass. I covered this in my vacuum decay video too, and I'll put a link in the description. We can also see here the particles called the gauge bosons. These are the particles that carry those interactions. The force-carrying particle for the strong interaction is the gluon. Gluons bind the quarks together to form protons and neutrons, and I'll delve a little deeper into the relationship between quarks and gluons in my quark video, which will be the next video that I release on this topic. However, with my work schedule, I'm not sure when it'll be coming out, but if you click the little bell icon thingy, you'll be notified when it does. On to our next interaction, which is the weak interaction. And whilst the strong interaction is responsible for holding things together, the weak interaction is responsible for breaking things apart. More specifically, breaking atomic nuclei apart during radioactive decay. Atomic nuclei are strange and interesting things. Inside the nucleus of an atom are the protons and the neutrons. The number of protons determines which element it is. 3 protons gives us the element lithium, 6 protons is carbon, 8 protons is oxygen, and so on. There are also neutrons in the nucleus as well as the protons. Protons are positively charged, and neutrons have no electrical charge. As I've already mentioned, the positively charged protons repel each other because like charges repel. The protons don't like to be near each other and so want to split the nucleus apart. However, as I've already stated, there's a bit of the strong force extending beyond the protons and holding them together and stopping them from flying apart. There is, however, only just enough attractive force between them. Also, the neutrons have no electrical charge and so aren't repelled by anything, but they do have the residual strong force that holds things together. This means that to keep nuclei stable, all elements apart from hydrogen haven't got just protons in the nucleus, but also neutrons. And it's these neutrons that help to hold them together and keep them stable. This is because that even though the neutrons aren't being repelled by anything, they do have the residual strong force helping to hold everything together. For elements with small nuclei, there tends to be roughly the same number of protons and neutrons, and this seems to be enough to keep them stable. However, as nuclei get bigger, there needs to be more and more neutrons to keep that stability intact. And even so, as the nucleus gets even bigger, it can't keep all the elements stable. This means that the nuclei of some elements undergo nuclear decay in order to turn into more stable substances. That's quite a bit of a simplification, but it'll do us for our purposes. This then is where the weak interaction comes into play. There are many nuances to this, but to keep things relatively straightforward, I'm going to consider a type of radioactive decay called beta decay. Sometimes, if a nucleus has too many protons or neutrons, it can change one of them into the other, and this is beta decay. Again, like the strong interaction, there are force-carrying particles associated with the weak interaction. These are the W+ boson, the W- boson, and the Z0 boson. The W+ and W- bosons both have an electrical charge, and the Z0 boson doesn't. During a type of radioactive decay called beta- decay, a neutron turns into a proton. Now, a neutron has no charge, and a proton has a positive charge. So in order to maintain the charge, in order to conserve the charge, the proton then emits an electron and an antineutrino. The electron is negatively charged and makes sure that the overall charge is conserved. So why does an antineutrino also get emitted along with the electron? Well, the loss of the electron conserves the charge, as I've already said. We also need to conserve the lepton number. Now, as I've already mentioned, leptons are particles such as electrons, as can be seen here in the standard model. The neutron is a particle with a lepton number of 0. The neutron is made up of quarks, and quarks aren't leptons. So the overall lepton number of a neutron is 0. This then decays into a proton. This also has a lepton number of 0, and an electron. Now that's a lepton, so now we have a lepton number of 1. Thus, in order to conserve the lepton number of 0, a particle with a lepton number of -1 must also be produced. And this is the antineutrino. This is the antiparticle of a neutrino, and so therefore the lepton number is -1. But what's actually happening inside the neutron to make all this work? And where do the force-carrying particles come into it? Well, if we look inside a neutron, we can see that it's made from 3 quarks, 2 down and 1 up. And these quarks have an electrical charge. The up quark has a charge of +2/3, and the down quarks have a charge of -1/3. This makes the neutron neutral in charge. In β- decay, one of the down quarks changes into an up quark. In order to do that, the down quark must gain +1 to its charge, and to conserve the charge, the down quark, as it turns into an up quark, emits a W- boson. The W- boson has a charge of -1, but that very quickly then decays into an electron with a charge of -1 and an antineutrino, and this again conserves the charge. β+ decay is similar but opposite in a number of ways. In this process, a proton decays into a neutron, and a positron and a neutrino are emitted. The change of the proton into a neutron means that the proton has lost a +1 charge, and so to conserve the charge, the positron that is emitted has a charge of +1. The positron has a lepton number of -1, it being the antiparticle of the electron, and so to conserve the lepton number, a neutrino is emitted, which has a lepton number of +1. Again, looking more closely at what's happening inside the proton, a proton is made from 3 quarks, 2 up and 1 down. The ups having a charge of +2/3, and the down having a charge of -1/3. This gives the proton a +1 charge. In β+ decay, one of the ups changes to become a down. To do this, it must lose a positive charge. This positive charge is carried away from the up quark by a W+ boson, which has that positive charge. This boson quickly then decays into a positron with a positive charge and a neutrino with no charge. Without the ability for protons to turn into neutrons, then nuclear fusion wouldn't be possible, and elements heavier than hydrogen wouldn't exist. The universe would just be full of tenuous hydrogen atoms, dark and starless. Now on to our third interaction, called electromagnetism. This is the interaction that happens between particles with an electrical charge. It also governs our ability to see things. It's electromagnetic waves that interact with chemicals in our eyes that allows us to see. Electromagnetism is the reason that like charges repel and opposite charges attract. And to look at this force, we again need to look inside atoms. And here it's all going to start getting a bit quantum. The force-carrying particle of the electromagnetic force is called the photon. Yes, these are the particles that are responsible for visible light, X-rays and radio waves. However, just like with the other forces so far, we're here talking about virtual particles. These are particles that are produced but only last for a tiny fraction of a second. Normal photons of light, the ones that we can see, have a lifespan of billions of years, hence the reason we can see light from very far away galaxies that has taken billions of years to get here. A particle, and here I'm going to use the term real just to distinguish it from a virtual particle. Anyway, a real particle is just a quantum fluctuation in a field. I talk about fields in more depth in my vacuum decay video, so again, link in the description. Real particles are fluctuations with a specific amount of energy. These real particles are constantly emitting virtual particles. These virtual particles are quantum fluctuations in a field that don't have the right amount of energy to be a real particle. They're produced and are very quickly reabsorbed. Here we can see an electron. It's producing a whole cloud of virtual particles that are produced and quickly reabsorbed. Now, these virtual photons, whilst they have no mass, they do have momentum. As a virtual particle is released in one direction, this pushes the electron in the other direction. But because these particles are being released in all directions simultaneously, the overall effects are cancelled out. Here we can see two electrons. Electrons are negatively charged, and therefore they will repel each other. And the electrons are both releasing virtual photons. As the electrons come closer to each other, the virtual photons emitted by one electron can actually be absorbed by the other electron. And because of their momentum, this will then push the electrons away from one another. And for this reason, like charges repel each other. And that really nicely explains why like charges repel. But what about opposite charges? And here it's going to get even more quantum. And the more quantum we get, the more vague my explanation will get. I've done a bunch of research on this and I couldn't find anything even approaching a decent answer. The best I could find was a YouTube video from Joe McCulloch, who had a series on Ask a Physicist Anything. I'll put a link in the description below. So with particles of an opposite charge, even though they emit a bunch of virtual particles, and even though a particle might be travelling in this direction here, its momentum might actually be in the opposite direction. It's almost as if the particle is produced on the other side here and has momentum back towards the original particle that emitted it. This then means that the particles with opposite charges are pushed towards each other. I accept that this isn't the greatest of answers, but the real answer involves the Heisenberg uncertainty principle, wave functions, probability, and time. So for once, I'm just going to say it just does okay. And yes, I know that's really unsatisfactory. If anyone has a better explanation, leave a comment below and I'll pin it. One of the quests of modern physics is to combine these forces. It's thought that in the very early universe, during the Planck epoch, there was just a single force that governed the whole of the universe, tiny as it was. However, as time progressed, these forces split into the forces we observe today. At very high energies, the weak interaction and electromagnetism combine to produce the electroweak interaction. These two forces will unify above energies of 246 giga-electron volts. So at temperatures above about 10 to the 15 Kelvin, these two forces will unify. Unfortunately, we've only managed to produce temperatures of about 5 times 10 to the 12 Kelvin. That's about 200 times lower than the required temperature. So anyway, that's electromagnetism. And now on to our final interaction, and the one that I've left until the end for a number of reasons, and that's gravity. Now, gravity isn't a force in the same way that the other forces are. Gravity is the interaction between bodies that have mass. Any body in the universe that has mass exerts a gravitational pull on other objects, but the interaction that I'm talking about here isn't really an interaction. Gravity is produced by the property of mass in that it warps space-time. If you imagine the fabric of the universe like a rubber sheet, then a massive body on that sheet will cause it to warp. Objects such as planets that travel close to the massive body will follow a curved path because of the warping of space-time. This is what causes objects to orbit around other objects, like the Earth orbiting around the Sun. In reality, they both orbit around their common centre of mass, but since the Sun is a lot more massive than the Earth, the centre of mass of the two bodies actually lies within the Sun. The rotation of the Earth around the Sun will cause the Sun to wobble, ever so slightly. For two bodies with more similar mass, they will indeed orbit around an invisible point, which corresponds to their combined centre of mass, and this can be seen in the orbit of Pluto and its moon Charon. I know that the rubber sheet model isn't completely accurate, because space-time isn't a two-dimensional sheet of rubber. It's more a multi-dimensional grid of hyper-rubber or something. However, this model is easier to visualise. I've tried modelling this in 3 dimensions, but on a 2D screen it doesn't look good. Everything just gets in the way of everything else. Anyway, look, I'll leave a link to the video. It's the vacuum decay video again, and that shows you what it looks like in 3 dimensions. But honestly, rubbish. This means that gravity is quite a bit different to the other forces. All the other forces exist as a result of the exchange of virtual particles, but gravity is different. There's no virtual particle for gravity. Well, actually, we haven't found one. One has been postulated called a graviton, but up to this point, no gravitons have ever been detected. That doesn't mean that they don't exist, though. We might just not have generated enough energy to produce them. One of the most intriguing aspects of this property is that mass, and therefore the gravity exerted by it, is very similar to acceleration. Let me explain. Imagine I'm sealed in a completely closed box with no windows, so I can't see out. If this box is on Earth, I'll feel a force pulling me downwards. This force is the gravity produced by the mass of the Earth. Imagine now if that box were moved so that it was now in deep space, far away from the gravitational influence of any stars or planets. But imagine that the box is accelerating upwards at a rate of about 9.8 meters per second squared. To me, inside the box, I wouldn't be able to tell if I was stationary on Earth or accelerating upwards. To me, on the inside of the box, both would feel exactly the same. Not only that, but we know that travelling at speeds close to the speed of light has a time dilation effect. In fact, travelling at any speed has a time dilation effect. It's just way too small to imagine at speeds lower than a significant portion of the speed of light. Gravity also has a time dilation effect. A clock placed closer to a source of gravity will run slower than a clock placed further away. Gravity is a fascinating phenomenon, and I plan on making a video just on this force. So I'm going to leave gravity here and come back to Earth. Anyway, thank you for your patience in waiting for this video to come out. And for now, and until next time, thank you for watching.